You. Okay, so today we are going to finish up talking about how fancy kinetics. Oh, I must have screwed something up here. Oh, because I'm in the highlighter with black. It does look kind of neat.
Right.
Okay, so last time we learned about what is called the rate expression. And sometimes it's also referred to, so AKA the rate. You don't have to rewrite this again. I'm just writing this to organize my thoughts. The rate with respect to change in concentration. I usually like to go with the rate expression because it's less words and it's less hassle for me to write down. But remember the rate expression, so if we have something like H2 plus, that's stupid, H2O, so we would have to put a 2 here and 2 here. Your rate expression looks like this. Do you remember doing this from Wednesday? Super. Okay, so then we can write this out for only one item in our reaction, or we can write it for all of them. Many of you have shown me what your homework looks like to have it checked, and so that's good. It seems like for those of you who have gotten it checked, it's looking okay. Now what we're going to learn today that is new is something called the rate law. The thing that makes kinetics confusing is that you are not using like different words to describe anything. There's the rate law, there's the rate expression, there's the rate with respect to change in concentration, and all of these words sound so similar that it makes it more difficult than it really has to be, than it really actually is. Okay, so I'm going to show you what the rate law is now. If my pretend chemical equation looks like this, where I have two reactants and two products, this is how you will write the rate law. I'm going to write it down first and then I will explain it later. The rate equals K, that's a cursive K. Do you guys still have to write cursive when you're little kids?
Yes.
Did you? Okay.
With Mr. M.
Oh, I love Mr. M. He's such a nice guy. Okay, so K is the rate law constant. And just like every other constant, every reaction has its own unique rate law constant. And they have all been already discovered by the old guys whose life work is in the chemistry Bible. But now, let's take a look at what else we have here. Here we have M and N, and they are both exponents. So we'll go over a little bit to remind us about exponents here in a little bit. But notice how in your pretend chemical equation, there's no such thing as an M or an N anywhere. So where do these exponents come from? Well, first, let me tell you what they are. This is called the reaction order. And the reaction order is always a whole number. And it's usually like first order, second order, third order, etc. So M and N are both integers, they're whole numbers, and they're going to be for like the number 1, 2, or 3. There are some reactions that have a 0 order, but we won't talk about that in this class. If you're taking AP Chem, then we will. Okay, so where do they come from? You can only know what M and N are, like if their number is 1, 2, or 3, based on experimentation only. So I'm going to write on the board, can only be found from experimentation. Not stoichiometry. You can only find M and N by doing experiments. You cannot find them by looking at your chemical equation. So what does this mean? If you want to know what the reaction order is, you have to do a bunch of experiments and then change the amount of reactant that you're starting with. So maybe it's kind of a lot of like trial and error. You would try one thing and then you would make an adjustment and try it again and measure how fast or how slow the reaction is going. That's the only way you can determine what these exponent values are. You cannot just look at a balanced chemical reaction and say, oh, there's a 1 in front of the A, it must be first order. Sometimes that's true, but only because of coincidence, not because there's any correlation between the stoichiometry and how the rate law is actually found. This is one of the things about science that makes me irritated. And so Michelle and Matthew and Sienna, you guys were at my little talk about science and God and everything. This is one of the things that makes me feel like it's easier to believe in God than it is to believe in science, because believing in God just is a choice that you make in your mind. Yes, God exists and there is a power that is greater than us that created the world. This relies on so much more faith than just making that conscious choice, because you have to believe all of these things that are so arbitrary and esoteric. And the only reason that we're saying that this is a rate law is because we manipulate all of these facts that are happening to make the math work. The reason you have to use a constant here is because this is not perfect, but we call it a law. And so in my mind, when you hear people talk about this is settled science, or the science doesn't tell us that God exists. Science is pretty shitty to begin with. And if you have to have this much faith and this level of manipulation to make your numbers work, is it actually what we think of as science? Maybe not. So this is arbitrary, it's a little esoteric, and it's very let's think through thoughts in our minds. So then if you're given a problem, how do you know what M and N are? You have to read. So I want you to pull out your homework number 8, please, and turn to the last page, because there are some examples on there. For example, number 5. Number 5 asks us to write the rate law, and then it'll tell us in the problem what the reaction orders are. Yes, Rowan?
I don't have the
Okay. Why do I only have one left? I must have lost my copy. That's right, you can have this one. Okay, so number 5 says, wait for it. Oh. It's the reaction with ozone, right?
Yep.
So 2O3 yields 3O2, is that true? Mm-hmm. Okay, good. And then, so your problem there will tell you to write the rate law. Now, notice how when I did this here, I only included reactants. Products are usually, and for our purposes in this class, never. Products are never included in the rate law, because we're not worried about how fast they're made. We're worried about how fast the reactants are used up. Okay, so all of the rate laws look the same to start out with. It's always rate equals K times the concentration of your reactants. And in this case, we only have one reactant. But now remember, we cannot find what the exponent is for O3 by looking at the chemical equation. We have to read the words in the problem. So what does it tell you? It says it is something order with respect to O3. What does it tell you that that order is? It's second order. So here, coincidentally, these numbers are the same. That is not always true. Okay, but then your problem asks you for something else. What is the overall reaction order? So I'm going to go back over here. We'll try the blue. In order to find the overall reaction order, you are going to simply add up those numbers that are the exponent. That's it. So what is the overall reaction order for 5A? Well, there's only one exponent, so 2 plus nothing else is 2. So the way that we would write that, we would say it's overall second order. Joseph, I'm just going to lurk on yours. Okay. Let's do the next one as well. Write the rate law for this equation. So you can always get started in the same way. It's just like before, they're all the same. The only thing that's different is you have to know what the exponents are, and your problem will tell you that. So give that a read. What does it tell you that the reaction order is? So it should say the reaction is, somebody help me.
First order H2 and third order N2.
Okay, so it's first order H2. So that means that there would be a 1 here. And third order N2, there would be a 3 here. But remember, we don't ever write the 1 in exponents in math, right? So that's not a thing. So do you see how here on this reaction, actually your numbers are flip-flopped in like from the stoichiometry. So you would think that if you were looking at stoichiometry that the exponent for the N2 should be 1 here, but it's not, it's 3. So you just have to pay like attention to those things. Now, if I had to figure out also what was the overall reaction order, what would that number be?
4.
Correct. And the way that we would write that is fourth order. How did we find that? We just did 3 for the N2 plus 1 for the H2 is 4. Does that make sense? Okay, good. Good, because I'm going to absolutely destroy your world now.
No.
Okay, so let me see. I think I'm out of note cards. I have note card pirates that like to come. Oh, oh. Wait a minute. Okay, I might have enough. So what I'm going to do is give everybody a note card so that, Logan, you can start your note card for your test today. Because you'll want to have this written down. I don't have even any like colored sheets for you guys for this unit. I know. I think I've given you all the colored sheets there are to give. I know. I know. I know. So what I want you to do is start by, let's start making our little test note card. Don't lose this.
Logan.
Yes, Logan, don't lose this. All right, what color we got? We got blue. Let's make it black. Okay, So what we're going to do is we're going to write on the top of our note card, rate law calculations. Okay, so what's really nice and useful about knowing information about your rate law, you can predict how your rate will change by changing the concentration of your reactants. So we're going to make a little bit of a table. Don't copy it until I tell you, because I'm thinking this through in my mind as I go. I've never done this before, but this seems like a good idea. So we're just going to go with the Holy Spirit, but he hasn't provided all of the details yet, so let me just think it through. Okay, so we want the reaction order over here, I think. So don't write this down yet. Let's do, if we 2x the thing, 3x the thing, 1/2 the thing. All right, still don't write anything. Okay, hang on. Still don't write anything. Okay, so this is what we're going to do. If we have a reaction that is first order, how will that look? That will look like rate equals K times X to the 1, which we won't write. Okay, so let me just get the first row of the table in, and then I'll tell you to copy it. I just want to make sure that this is like in the most logical way possible. Okay, so let us say that we are multiplying the initial concentration of X by 2. What will happen? So in other words, on this table, we are going to, let me just think this through here for a minute more. On the first row, in the second column, if we have to double the concentration of X at the beginning of our reaction, what will that do? Okay, so when we're very first starting out and we have a regular amount of our, whatever our starting material is, we are always going to be comparing the rate to the number 1, because that's always going to be our starting place. So no matter what exponent you take the number 1 to, it's always itself. So we're always going to be comparing it to the number 1. So what we want to do is like put, however we're changing our concentration of our reactant, we just want to put this number into, oh, and I think, nope, okay, that's just on the TV, okay. I'm really worried about that. Someday I'm just going to like start writing with the marker on the TV. What we want to do is put this number into this equation. So what will that look like? It will look like rate equals K times 2 to the first power. What is 2 to the first power? 2. Okay, so if we have a reaction that's first order and we double that reactant's concentration, how will the rate be changed? It will increase by 2x. In other words, the rate will be doubled. Okay, so let's see what happens then if we triple the concentration of our reactant X. So we're just going to put that into our formula here, and so we don't really need to worry about what K is. It's not changing throughout. So 3 to the first power is 3. So if you have a reaction that's first order and you triple that reactant, you should expect the rate of your reaction to also be tripled. So then what would you predict would happen if you only were using half of that same ingredient? How should your rate be changed? Joseph?
Divided by 2.
It should be a half, right? So I'm just going to write it'll increase by a half, but like just think about that as like it really will actually decrease. Okay, I think this makes sense. I think you can write this on your note card. We're going to have 4 rows of the note card. So however you want to do it, however you want to space it out, it doesn't matter to me. Some of you write really big. Some of you write really small, but nobody writes as small as Heaven. It's amazing how small her handwriting is. I was writing pretty small in my notebook yesterday, and Lindsay's like, "How do you write so small?" And I was like, "Oh, I have a really fine tip pen." But then in my mind, I was like, "Nope, nobody. This is not small compared to Heaven." Her paper saving is amazing.
I really just wonder, like, how can she make it move like that and get it to...
She must have incredible small motor skills. Like that she's just able to write that small. Her skills are just better than everybody else's. I mean, I feel like I can write small. I can't, and like neatly. And her handwriting is so consistent too. That's what makes handwriting look beautiful. It's not like how curly or anything you make it. It's how consistent it is. Like from one letter to the next. That's what makes it visually appealing. Oh, yours handwriting is not bad, Connor.
That's not good. You should see John Dozo.
That's pretty good.
He writes in Japanese half the time.
Is it that bad? Oh, ouch. Oh, ouchie.
Or Chinese, whatever.
That's not that bad.
Yours is not that bad, but it's sometimes bad.
It's just big.
I had to take points off of Victor's work the other day because his handwriting his like zeros were looking like real life 6s. And I was like, dude, I don't know what this is. Sorry, man.
My aunt called my handwriting good, and I was like, no.
If you take your time at your handwriting, Sienna, it is good. When you are like rushing through, it's illegible.
Yeah, that's what I think.
It's illegible.
I compare it to like the scratchings of an insane old man.
I love how you go to like the old man. That's great.
Yeah, I feel like it just adds to how bad it looks sometimes.
Like if your handwriting is big though, as long as it's consistent, it doesn't have to be tiny for it to be visually appealing. It just has to be consistent. I mean, unless you don't care about it being visually appealing. Some people don't.
Sometimes I can't read it. When we're playing bingo in Spanish, I'll need to take a minute and read my stuff out loud because I can't read my own handwriting.
Yeah, it's a real thing. Okay, so is everybody done copying?
No.
Okay, I know. I told you to wait while I was doing this all myself, so no problems, no problems. Anybody have nice plans for the weekend?
Baseball practice.
Oh,
Saturday.
yeah.
Damn.
Yeah. I'm gonna have to be here all day tomorrow. I'm so far behind. I gotta write that dreaded exam for leadership, Matthew. I was here early this morning because Jake had jazz band, and I was working from 7 o'clock till 7:45 with very little interruptions. I think I have 8 questions written,
Nice.
and I need to have 60
60 for what?
for the leadership test.
Right.
If it had to write 60 chemistry questions, half hour
Only?
probably. But I know how to do that. I don't know how to write multiple choice questions. Like it goes against my religion. It's against my religion.
How many children Candy
I
on.
like writing multiple choice.
How many children eat candy on what?
No, that's like your multiple choice question.
Oh, but like, in order to like properly write a multiple choice question though, you have to deliberately be tricky. Otherwise, like the answer is obvious and you wouldn't have need to have taken the class to answer the question. So like, to me, why bother? But I have to do it because it's this like St. Norbert College class, and that's how the professor writes his tests. So I feel like,
60 questions.
yep, 60 multiple choice questions.
Wow.
That's like misplaced normal things. But hers is on the computer.
Well, I did that the first time. I made a Google quiz as my test, thinking, oh, this will be easy to score and everything. It was an absolute nightmare, and I probably spent 12 hours just going through the mistakes that like the Google grading made, and it was horrible. Never doing that again.
Just 2 quizzes.
No. Okay, so let's talk about what happens if you have a reaction that's second order, and now we're doing all of those same manipulations. Okay, so if we are going to double the amount of our x, what will happen to our rate? Okay, so here's our rate. Now, what we're going to do is put that 2 in for x and do the math just the way we did before. It's just a little more complicated now. So what is the number 2 to the second power? 4. So if you double the concentration of your reactant and it's second order, your rate will now go up by 4 times. Okay, so that's really helpful. That's a pretty good increase. What happens if you triple it? What's 3 to the second power? 9. It's not 6.
I almost said 6.
I know, this is a really easy thing to mess up in your mind. This is one of those things where, when my brother was in pharmacy school, they told him don't use your mental math for anything because you could have a bad day and do like 4 plus 8 is 16 in your mind, and you can you can convince yourself of anything, and that could be like life or death for a patient. Mm-hmm. So use your calculator for everything. So there's no shame in, I gotta make sure that my mind is working properly. 3 to the second power is 9. Okay, so then what would happen though if we would have to have that concentration? 1/4, good. So if you decrease the concentration of a reactant that's second order, you're gonna slow your reaction down considerably. I'm afraid of running out of room. Spaces make me sad. Okay, so let's do the same thing now for a reactant that is third order. If it's third order, our reaction should look like, or our rate law should look like this. So now, if you're going to double the concentration of X, let's put 2 into the math. What's 2 to the third power? It's not 6. It's 8. Okay, so that's a pretty big increase in the speed of this reaction here. What will happen if we triple the amount of that reactant?
47.
3 to the third is 27. Whew. That's like Miss Bishop driving on the highway. But if we have that concentration, 1/2 to the third power is 1/8. We might as well. I was just going to say, I don't think there are any fourth order problems on your homework, but let's do this one just so that we can think it through, and then you'll have the data if you need it. Rate equals K times X to the 4th power. Oh, oops. X to the 4. So if we double it, 2 to the 4th power is 16. 3 to the 4th power would be 71? I don't know. Let me, that was mental math.
81.
80, oh, damn it. See, I knew that couldn't make sense. 71 is not divisible by 3. And then if you do 1/2 to the 4th power, that would be 1/16 x. Okay, so let me show you how to use this. I don't have homework. So going to your homework on the last page, I believe that very first question is a question that asks you these types of questions. So that I think is question number 4. Can somebody please tell me what the reaction is for number 4? Or what the rate law is, maybe?
A times A second times B to the third.
A to the second and then B to the third. Perfect, thank you. Okay, so part A wants you to manipulate which of the reactants?
A.
A, and what are we doing with it?
Double.
Okay, so how do you use your note card? Pretty easily. What we're going to do is we're going to check out which reaction order it is. So it looks to me that A is in a second order reactant. I'm just going to go on my table then, and I'm going to see where it is that I am manipulating my starting amount. So if I'm starting with 2x, that reaction will increase, the rate will increase by 4x. So how should I write the answer? This is what I do. So in my mind, this says the rate will increase by 4 times. Did that make sense when I did that here? Okay, good. So what is B asking you to do?
The same except B.
The same except B. Thank you, Joseph. Okay, so find B's reaction order on the left column. We're doubling it. So what should happen to your rate?
You're supposed to do 4x.
What'd you say?
4x.
Nope.
8x.
It is 8x, right? Because here you're in third order, so that means you should look on this row of your chart. We're doubling it, 8x. What does C say?
A's triple.
Okay. Find that. Think about how your rate should increase. God bless you.
7?
It's not 27. What is the reaction order for A? Which row of the table are you on?
Second down.
2, yep. And so if we're going to triple it, that should be increased by 9x. Thank you for making that mistake, Joseph.
Ouch.
Honestly, it makes my job easier when I hear you guys make mistakes, because then I know what I'm doing a bad job of explaining. So it makes my job easier if you screw up. So screw up more.
Damn.
Does this make sense?
Yeah, makes sense.
Okay. Is there a part B for this?
Yep.
And what does it ask you to do? Is it B
Yeah.
to the 3x
Yep.
tripled?
Yep.
Okay, so then what should your rate be for this one, Joseph?
9x. I kidding. 9x. 727.
You're hilarious. That's correct. Okay, wonderful. So you guys have a good start on this. Don't lose this note card because it makes it so much easier to have this. We've already thought out all of the chemistry and we've put it here so that we can now simply just go back to reference this. Having this, there's no shame in having this and needing to use it because we've already thought through the chemistry. If you look at this and we don't ever practice this again until the exam in several weeks, you won't know how to use this. So having this is not helpful unless you know what you're doing. But you know what you're doing, so you should be fine. Is this helpful?
Yep.
Okay, good. All right, let us take a little brain break and then we're gonna start a new thing. So I'm gonna push a pause. I'm gonna stop this video now and start a new one so it doesn't take 8 years to upload on YouTube.